So this graph is called a phase diagram. Phase diagram. Now you'll notice that there are no numbers on this diagram, and the reason is because all the diagrams look alike, but the numbers would be different. So if we don't use numbers, then we can still talk about the graph without talking about what substance it is. So phase diagrams show a theme, and the theme is that molecules can only do one thing at a time. And so over here on this little column here, we're going to talk about what the one thing at a time is. Next, we're going to label this graph so that we can talk about everything. We're going to label A here, and B here, and C here, D here, and E here. Next. All right. So let's start by talking about A. So the way we read a graph is we start from the left and we move to the right. So I would say, as I'm putting heat, here's my heat, as I'm putting heat into my substance, my temperature is blank. As I'm putting heat into my substance, my temperature is rising. Okay. Okay. So next, we're going to go to B. As I'm putting heat into my substance, my temperature is constant. Right, staying the same. But I am still adding heat into my substance. So what is that heat doing if it's not raising the temperature, which it's clearly not? The temperature is not rising. No. So what is that heat doing? Because I'm still applying heat. It's sort of like if you have a pot on the stove, you're still applying heat, but the temperature isn't rising. So what's actually happening? No, that's a good guess, though. What? Yes, exactly. At B, the molecules are changing phase. And that's what's happening. The energy, and in this case, they're changing from solid to liquid. The energy that's going into the substance at this point is no longer changing the kinetic energy. Now it's being used to break those intermolecular bonds. And so, as it's breaking those intermolecular bonds, the molecules are moving to the next phase of matter. So in this case, it would be from solid to liquid here, all right? We call this place right here, what do we call this place? That point. The melting point. The critical point is the point where liquids no longer exist because the temperature is so high that it doesn't matter what pressure you put it under. That's up here, the critical point. So this is the melting point or the freezing point, depending on which direction you're going, right? The melting point or the freezing point. Now remember, we don't have a substance on this chart. This could be bromine. This could be carbon dioxide. This could be ethanol. This could be anything, all right? So, because all substances have a chart that looks like this. For some of them, this is really steep and short. For some of them, this is super long, okay? They can all be different sizes. But if this were water, so if water, then X would be equal to what temperature? Yes, excellent. 0 degrees Celsius. If this were water, that melting point / freezing point would be 0 degrees Celsius. Okay? Now, we've gotten to this point where we've gotten to where the molecules are changing phase from solid to liquid. And now we're going to keep going. So we're still going. And now we're still putting heat in. And what's happening to our temperature now? Right. So as we're putting heat in, now our temperature is rising. So at letter C, temperature is rising. And you can see this by the chart, right? As we put the heat in, the temperature is rising. And now we're at letter D. And what's happening at letter D? Is the temperature rising? No, it's staying constant. And so what's happening at letter D? Yep, the substance is changing phase. So the molecules are changing phase. And in this case, they are changing from liquid to gas. That's right, which makes this point here, if I bring this over, that point here is called what? Yep, is called the boiling point or the condensation point. The boiling point or the condensation point. And then we go from here where everything has to turn into a gas. We're going to go to letter E. And at letter E, the temperature is going to rise again. Now, if this were water, what temperature would be letter Y? Aaron? 100 degrees Celsius. So Y would be equal to 100 degrees Celsius. So this corner is the boiling point, and this corner is the freezing point. So are there any questions about this graph? Okay, the last thing that we need to see about this, is this an endothermic or an exothermic reaction, and how do you know? Always left to right. How do you read a graph? Do you read a graph from the right to left? No, you read a graph from the left to the right. How do you read a book? Left to right. Left to right. Endo or ecto? Endo. How do you know? Because the energy is getting put into the substance. Right. So the temperature is rising and the energy is being put into the substance. The heat energy is being added into the substance. And the temperature is rising. So this is an endothermic situation. All right. Now, if you're curious as to how am I going to know if it's endothermic or exothermic, how am I going to know? So just ask yourself. Here is a graph where we have reactants and products. Substitute the word carbon for energy. Carbon, adding more carbon. Okay? Which one has more carbon? The reactants or the products based on the graph? The products have more carbon. So did you have to add carbon in? You did. So is it endocarbon or exocarbon? Endocarbon. Because I had to add carbon in to get my products to have more carbon than my reactant. Obviously, there's no carbon in this reaction, so this is just like a little example, right? Okay, just substitute the word carbon and then ask yourself, if this was a reaction with carbon in it and the products had more carbon than the reactants, would I have to add more carbon? Yes, you would. Okay, so let's look at this one. Here, reactants, products, right? Now, lots of carbon, not so much carbon. Is this endocarbon or exocarbon? Well, this would be exocarbon, wouldn't it? Because carbon must have been released here. We don't know where it went, but carbon left because there's less carbon here than there is here. Do you see how energy is just like carbon? Does that make sense? Okay, same thing here. Lots of carbon, not so much carbon. Carbon left. Does that make sense? There's, by the way, no carbon in these reactions, but you get my point. Just used carbon instead of energy. Lots of energy, not so much energy. What happened to the energy? The energy left. Exothermic. Okay?